Hey everyone, it's my pleasure to present you the work we did with Anthony Papavassiliou on models and algorithms for clearing integrated TNG markets. So let's start with a bit of context. As you may know, historically, the transmission system is operated by the TSO, and this is where the power is generated. And the distribution system is consuming power through households. And the way we cleared the market in the past was that we aggregated the distribution load and clear the market at the transmission level. But now, with the integration of renewables such as wind or solar PV, power can be generated on both transmission and distribution side, which means that we need to reorganize the way we organize electricity markets. So now distribution system must be integrated in the way we clear the markets. The GSOs will have a more active role in the coming years. And also the distribution systems are more complex to model. We have to account for losses, which is not always the case for transmission network. So distribution systems must be modeled more carefully. And the scope of our work considers European balancing markets, and we will have a detailed modeling of the network. We will allow for a complex bit structure on the market, and also we are limited in time since we are considering balancing markets. So now that I provided a bit of context, I'll explain what type of integrated TNG balancing markets problem we are solving. We'll consider two centralized and one decentralized approach to solve this problem. We'll show a bit of numerical illustration and conclude the work. So these are the following assumptions we make on the work. So we'll consider real-time markets, which is activating transmission or distribution reserves to adjust a predetermined dispatch coming from a day-ahead market, for example. We'll consider a 15 minutes time horizon, a 15 minutes steps for a 1 hour time horizon. So we'll have 3 or 4 time steps. The transmission network is supposed to be meshed, and we will be able to use the DC approximations of the power flow equations. This transmission network is linked to a distribution network through a line, and the distribution network we will consider that it's radial, so as a tree, and we will use the true ACOPF equations. And the goal of this work is to implement a practical clearing platform capable of ensuring so optimal decisions or near optimal decisions, physically feasible dispatch. It should also be able to return coherent prices, so locational marginal prices, even if we have complex bids. And we impose a time limit of 5 minutes. Okay, so now let's have a look at the problem we're trying to solve. So we're trying to minimize activation costs, subject to transmission constraints, distribution constraints, interconnection constraints, and bid and intertemporal constraints. I'll explain each of these constraints in the coming slides. So let's start with transmission constraints. As I said, we were allowed to use the DC approximation on the transmission network. So we will only have real power decisions, so real power injection P, real power flow FP, and theta, and the angle theta. And we will separate the constraints into, so real power balance constraints, so FTN, XTN equals 0, associated with a price, so that will be the MP for the transmission network. And the rest of the constraints are in a set omega Tn, and we typically have line limits or generation limits here. Okay, for the distribution constraints, we'll use AC power flow equations or the SOCP relaxation. So in addition to real power decisions, we also have reactive power decisions, so Q. And we also need for losses to account for voltage magnitude and voltage angle theta. And again, we split the constraints into two types. So either operational limits like line limits, etc. And we will have a real and reactive power balance denoted in this FGN, XGN, and associated with a price lambda GN. And when we will use the SOCP relaxation, we will denote the set omega, such as tilde omega GN. For the interconnection, we will assume that we have a transmission line. So for the decisions for this line are typically FP and theta. And for modeling purposes, we'll just assume that we will duplicate the interconnection variables, and we will have so the Z variable linking what's going on in the transmission network, and another constraint linking to what's going on in the distribution network. Since Z will only appear on this constraint, and we will sometimes use the dual information of this constraint, we have the following relation between these two constraints via mu. And for bit constraints, we will assume the following. We will assume that we might have block bits. We'll assume that some bits can come with exclusive acceptance rates. But for example, I submit three bits, but only one of them can be accepted. A bit can also have a minimum duration, etc. So I won't enter all the details. And we also have some common interpolable constraint like ramp constraints. So for our problem, this will lead to additional constraints on the network and the introduction of binary variables y. That's why now x is also linked to y for both transmission and distribution, and y is a binary variable. Okay, so now we can write down the problem. So as I said, we're trying to minimize some activation costs, both on transmission and distribution level. We have the operational constraints linked with also the binary variables for both transmission and distribution. We have the interconnection constraint written like this, and we also have the power balance for the transmission network and power and real and reactive power balance constraint for the distribution, and the fact that y are binaries. And this obviously leads to a mixed integer nonlinear problem. And to solve this problem, we will assume three practical approaches, one based only on relaxation, one which we will call a benchmark and allows us to have feasibly physical dispatches. And since in practice, one operator has not access to the whole transmission and distribution network, we will propose a decentralized method based on a residual supply function. Okay, so for the relaxation approach, what we assume is that we make SOCP relaxation of the AC power flow equations in the distribution network. And we will solve this problem in two steps. First, we solve the semi-SOCP in order to get the binary variables. And then we solve the same problem, fixing the binaries in order to get the dispatch decisions and the LMPs. And this is motivated by IP pricing introduced by O'Neill in 2005. Then in case we don't have a feasible dispatch from the relaxation, we will assume that we recover a dispatch by writing down the true ACOPF equations and fixing the same binaries, and we will get the dispatch decisions that are now feasible and also prices, because we will solve this problem using inter-point methods. So we can switch to the decentralized approach based on RSF. So to do so, we will assume that we have a range of potential values for the interface flow. And for each of these potential values, we will solve the associated distribution problem. So in a way, what we want to do is to aggregate the distribution system at the transmission level. And what we solve concretely, so we fix the flow, the interface flow. We will assume that we have an SOCP relaxation of the distribution equations. We will assume that we relax also the binary decisions. And for each level of flow, we will solve this problem and we will store the associated dual variable in order to have an idea of the valuation of the flow at the interface. Once we did that, we can build the residual supply function as such, aggregate the distribution system at the transmission level, and solve and clear the transmission market, basically. And to do so, we have the same problem for the transmission. And we will add this term reflecting the what's going on in the distribution system. And also we define the flow, we discretize the flow as we did before. And now Z is a variable and needs to be determined by the transmission system. Now that we clear the transmission system, we can easily clear the distribution system by fixing the interface flow, and we keep the same equations in the distribution. That will allow us to have the dispatch decisions for the distribution system. And in order to be sure that we have coherent LMPs, we will resolve a transmission and a distribution problem where we will have now considered that the binaries are fixed, but dispatch decisions are not known, and we slightly correct the objective function by using the interface price that we computed. And this is the safest way to recover coherent LMPs. Now we can discuss the numerical illustration to see how efficient the methods are. We use the dataset built for in the scope of SmartNet project, which is based on an Italian test system. So we have the first test system, which is kind of a toy example where we have a small network and a small amount of bits, and two other systems that are more realistic. So, and to make the comparison, we report several things. So we have each of the methods, and so RSF 100 is the residual supply function with 100 points, so 100 points on the range of potential value at the interface. We report the solve time. Between parentheses, it's an ideal solve time if we parallelize the approach, the RSF approach. We report the objective function. We report the percentage of lost opportunity costs. Lost opportunity cost, if you don't know what it is, we can assume that it's what you would need to pay to a generator or an operator to make them do a particular decision if it's not optimal. And we report also the maximum violation on the constraint. So we see that for the small test case, the relaxation is already is more or less feasible. The benchmark also gave the same objective value, and the RSF approach give a near optimal objective with a small LOC. And for the first larger test case, we see that the relaxation does not give a feasible dispatch. The benchmark then allows to us, with a small increase in the objective function, recover a feasible dispatch. And we also saw that the RSF is still promising. So we have a near optimal objective, a small amount of LOC, and a feasible dispatch. And this tendency is confirmed within the largest test case, where the objective functions stay within a reasonable range. Again, the relaxation does not give a feasible dispatch, while the RSF and benchmark give promising results. Also, the time reported in parallel here is obviously too optimistic. So we also wanted to show that with a reasonable amount of processor, you might solve in the RSF approach in 1 or 2 minutes. That being said, we have developed and implemented centralized and decentralized approaches to tackle the integrated TNT balancing clearing markets. And the preliminary results show promising outcomes. So future direction of the work will clearly provide the theoretical guarantees of the success of the approach, also test the approach on other test systems, and finally suggest how settlements should be done in such a framework. Thanks for listening, and I'm happy to answer your questions.